In this video, I want to review some things we've talked about before, and then show some new calculations, and then talk about continuous random variables. So, the lifespan of light bulbs approximately normally distributed with a mean of 1,000 hours and standard deviation of 125 hours. Let X be the number of hours a light bulb lasts. So, I'm going to draw one picture here. Again, you'd probably, you'd have to draw it multiple times, but it's normal. 1,000, 125, and then let me try and color coordinate this. So greater than 1,050, so probably 1,050 is up here. So I'm going to do this one in red. Okay, so then you put your 1,050 and shade. Okay, and I'll drag the answer in a second. 750 down here. Okay, so less than 750. And between 800 and 1,000, so like this, 800 and 1,000. Okay, and again, I did this with the calculator using normal CDF, so let me drag those in and you can check those answers over real quick. You can see, remember we always do lower bound, upper bound, mean, and deviation got cut off. So there's your answer for the red. Lower bound, upper bound, mean, standard deviation. There's your answer for the blue. Lower bound, upper bound, mean, standard deviation. There is your green answer. Okay, let's move on. Concessionaires estimate that attendance at a football stadium will be 60,000 people on a clear day, 45,000 if there's a light snow, and 15 if there's a heavy snow. Furthermore, from past years, the probability of clear-sized light snow or heavy snow on a particular day is estimated to be 0.5, 0.3, and 0.2 respectively. So X equals, so X, this random variable, I'm defining it as the attendance. Okay? So the possibilities are 60,000, 45,000, and 15,000. Our probabilities are 0.5, 0.3, and 0.2. So what I've just written here is the definition of my random variable, and then the probability distribution for that random variable. Now, I want to calculate the expected value of this. So I'm going to write expected value of X. If you remember, how we do that is probability multiplied by random variable plus probability multiplied by random variable plus probability multiplied by the random variable. So if you type this in, you get 46,500, which is not one of the possibilities. And we talked about this in a previous video, that what you need to remember, that the expected value here is really the mean. And people are never surprised when the mean isn't a possible outcome. The average on that quiz was 7.31. People aren't surprised that no one got a 7.31, but for some reason this throws people, that the expected value is not one of the outcomes that the variable can take on. Okay? All right. Along with the expected value, I just wanted to talk about, because we have an average, we should also think about how we measure spread. Okay? So our deviation, okay, the way we do deviation for a random variable like this follows this formula. Okay, it's the square root of the sum of the probability of a random variable minus the expected value squared. This is very similar to, with some algebra, changes to our original standard deviation formula. And let me write down then what this would look like for this particular example. We would begin by doing the probability, so 0.5. And then 60,000, since that's the random variable, minus the mean. And we square it because, of course, we don't care above or below. We want positive answers. The next will be a 0.3, and then 45,000 minus 46,500, and then 0.2. And our random variable minus 46,500 squared. Okay? And once we have that, then we simply do the square root, because of course squaring made these numbers quite large. This comes out to be in the 17,000 range, okay? It's like 17,034, I believe, which it's a little large considering that, you know, our mean was 46,000. Going up 17 puts us over the maximum attendance, but you've got to remember it's also trying to reach down to the minimum attendance. So the 17 it's a reasonable answer based on the spread of the data, okay? This is a formula to know. Okay, probability random variable minus the expected value squared, and then the sum, and then the square root. So, in a previous video, we talked about discrete random variables. Discrete random variables are variables that have a known set number of outcomes. The problem we just did with the concessions, there were 3 outcomes: 60,000, 45,000, 15,000. That was it, 3 outcomes. A continuous random variable is one with an infinite number of outcomes. The light bulb problem had an infinite number of outcomes. A problem we did on a previous video dealing with the normal curve about the amount of rainfall in a month in Minnesota. That has an infinite number of outcomes. Just because we've never had 35 inches of rain in a month doesn't mean we may not. So thinking kind of a big scale, there are an infinite number of outcomes. So the variable, to find the probabilities, we evaluate a density curve, just like we have been with the normal curve. This is for my calculus folks. The continuous random variable then is given by a function, the density function, and the area between negative infinity and infinity is 1 because it constitutes the entire sample space. The probability between A and B is simply the area of my density function between A and B. So we've already done an example with the normal curve. I want to step back and do an example off the calculator. The rand function. If you remember, the rand function in your calculator generates a random number between 0 and 1. Now, of course, the calculator, to the amount of digits it gives you, there actually are a finite number of numbers because of the lack of an infinite number of decimal places. But theoretically, how many numbers are between 0 and 1? It's infinite. So x, my random variable x, is defined as a number chosen using the rand function on the calculator. So the probability that that number is between 0.2 and 0.9. So think about, if here's 0.2 and here's 0.9, what's the probability of being between there? It's the area, so it's 0.7. The probability of being above 0.65, okay, so now we're talking that area, and that's 0.35. So again, we've been dealing with density curves, so I'm not going to do a lot of examples here in this video, but we use area to do it because there's an infinite number of outcomes. So if I said to you, what's the probability that x lands exactly on 0.5? Well, the answer is 0 because there are an infinite number of outcomes. So it's like saying, well, what's the probability you pick one number out of an infinite number of outcomes? The probability of that is 0.